G'day viewers. In this segment I'll talk about real-time transport in which information needs to be sent across the network in a timely fashion to meet a deadline. So when I say real-time transport, I'm really talking about something like a VoIP call, where voice or a video call, if video has been sent over the network with timing deadlines. And the reason it has timing deadlines is there's a person waiting at the other end to hear that call. So this is typically live information, and it's also interactive here, whereby two or more parties are communicating, so we need to turn around information quickly. You could just think of a telephone call. We're just trying to do it over the internet. What we're going to talk about in this segment is how we can provide real-time transport to run that VoIP call using the best effort service of the internet. And the technique I'll tell you about to make it work is the playout buffer technique. So the real challenge here is how to deal with network delay. We'll just think about one direction of transfer, even though in a real VoIP call information is being sent in two directions, and that's important for understanding the timing deadlines. So in the one direction, we'll go here from a microphone over on the left of the picture through the network to a speaker over on the right hand side of the picture. Now the way these real-time media work, voice samples in this case, is being produced at a constant rate at the source. It's going across the network and it's then going to be consumed at a constant rate at the receiver. The network is in the middle of all of this. So the network is going to add delay as packets go across it, so the consumption must be at a later time than the production. And the network also needs to have enough bandwidth. If we can't get the data through the network, well, you're not going to be able to make that VoIP call. But even when there is enough bandwidth, we need to deal with the delay. So let's think a little more about the delay through the network. A key attribute of this delay is that it's variable. This graph here, this curve, the blue one here, it's meant to show you the delays, the network delays of sending information across the network. Now the network delay itself is going to have a few components to it. It's going to be the basic message latency, that's what's shown here. This is really the propagation delay and transmission, prop plus tx delay. So they're fixed delays that it just takes to send a message that distance over a wire. In addition to that, there's also going to be some queuing delay because these packets are queued up in FIFO queues in routers, and when those queues get big, there is going to be more delay. This graph here shows a PDF or probability density function of the delay. So it's really showing the fraction of packets which experience which delay. The biggest delay, the biggest fraction of packets experience about this delay here. You can see that many packets experience delays around here. And these are delays which are somewhat bigger than the basic latency that we get from sending the message simply over that distance because we're adding a bit by the queuing, but not too much. However, a small fraction of the packets, and that's out here where the fraction is lower, are experiencing delays which are much greater. So all of this addition from here out to here is queuing. Extra delay from queuing. Okay, so this is what network delay looks like when you send things over the internet. If you took a lot of samples, you would end up drawing a graph a little bit like this. The variability that you get when you send information across the network and you look at the delays at the other side is something called jitter. That's actually important for a lot of our VoIP calls. And you might imagine why, because it complicates playing out a VoIP call. If you get a message sample of voice which arrives at a particular moment, then at the next moment this next sample should arrive, but suddenly it takes a lot longer for some unknown reason, because it got caught in a queue. Then the next one comes out much more quickly. Maybe it even arrives sooner than the other one. This kind of complicates play out a little bit. So let's think about play out, because that's really what we're trying to accomplish here. This is a different kind of graph, which is drawing the timestamps for media on the y-axis versus the actual clock time. And so you can see this line here, sender generation. That is a constant rate. That line has a constant slope, so it's going up at a constant rate as media is being produced at a fixed rate at the source. Now, what would ideally happen here, this is the ideal, it's not what we have, is that when you produce some media, say it's this sample here. When you send it across the network, it's going to take some amount of time to go across the network. That is this distance here that's labeled network delay, so it'll take a while to come out. On the other side, if the network had a fixed and preferably small delay, such as this delay here, then we would end up receiving samples and we could play them out at the receiver as we receive them along this curve here. This is really what happens in the telephone network. We have samples going into a pipe. There's no queuing inside the telephone network. They come out and they're ready to go to the speaker on the other side, and hopefully the delay is kept small. So this is what we would like to do. But of course that's not what we have. Let's think for a moment about what we have when we send messages across the network and we get that variable delay. Well, here maybe is the line for just the basic message latency. That's this latency here. You're not going to beat this. This was the latency, not the overall network delay. So it's going to take longer than that for the information to come out the other side. And it's also going to be a little variable, as we saw in the graph. So maybe we'll get a curve like this. Something like that. I don't know. I made it up. You can see here the difference between the time at which the media is produced, and if we just go across horizontally to here, this is when it arrives at the receiver. So this is the network delay. For that particular point, it's quite long. And you can see down here, it's shorter for a different sample down here. Why? Well, we just got a little lucky there and there was less queuing. So we're going to get something like that. Here's a cleaned up picture. Here, a cleaned up version of that picture. And you can see, so the blue curve is the important one to remember because it's media arrival. Now we've got to work out what to, and so this is when the samples from the VoIP call, they were produced and sent at a constant rate. This is when they're arriving at the receiver. It's a little bit all over the place. Now we have to work out how we're going to play them out. And what we're going to do to play them out, the technique for handling real-time transport on the internet today, is to use what's called a play-out buffer. When the media arrives, we'll put that media in the play-out buffer, and we'll then draw from the top end of the buffer and play things out at a constant rate. So the media is going to sit in that buffer, and that buffer's purpose is to smooth out the variable network delay. Right? Really, the dimension of this buffer is really about jitter. It's for jitter. If the network delay were constant, when information arrived, we would only need a buffer of, one sample and we could send it straight to the speaker. But there's variability when it arrives. That variability is the variation in delay, or jitter as we've called it. The buffer is there to smooth it out so information can sit in the buffer and be drawn at a constant rate at the other end. Let's look at that in terms of our other graph, which just shows the media samples over time. Here was the generation at the source. They went across the network. So there was at least a minimum latency to go across there, and then there was an additional latency. This is meant to be all horizontal here, due to queuing. And you can see some things arrived quickly, some took a little longer. We then put them in the buffer and we play them out according to this curve, which is a line at the same slope, so they've been played out at a constant fixed rate equal to the source rate. Now what this means is that the pink area in here really represents how long samples stay in the buffer. That's its purpose. The buffer ought to handle that variation, and so if you get there early, you spend a longer time in the buffer. We can also see there's a deadline. If you arrive later than the playout date, that's here, then the media is not much use. The conversation has to go on. You can't pause it. That would be very awkward. You don't have any samples, so you might just sort of play a little bit of a noise or something. It's like there's a little bit of a glitch. But this information is arriving too late, and actually it's not useful. It might as well have not arrived because it's not going to help us play out any of this media. The time to play it has passed. So this is what a play out buffer, the effects it produces and how it works. We're also, now let's look at a play out buffer in this other graph. Here we're back to our PDF that's showing the fraction of network delay for the different packets. Here's the PDF curve again. What we're effectively doing with the playout buffer is choosing some upper bound on the on the network delay that we're willing to tolerate. Some things will have a larger network delay, or there might even be lost packets. I guess they're equivalent to having a very large network delay over here of infinity. Some number of packets will be in this tail of the PDF. For those packets, it'll be too late to be used in the playout buffer. So we are making a bit of a trade-off by setting this point. We're picking the largest acceptable network delay to pick this playout point. Here's a little more for how you can think about this trade-off, and this should be fairly intuitive just from looking at those pictures. If we choose to allow a larger network delay to be acceptable, then we're going to end up with a larger buffer, and of course we're tolerating a larger delay across the network. Well, sorry, it's not that we're tolerating a larger delay, we're playing things out after a larger delay. So we're adding to the time it takes for the information to go across the network and be played out. On the other hand, we'll end up with less loss. More information will arrive by its playout time, we'll have it, it'll be great. If we choose a smaller network delay as the largest acceptable network delay, then we'll use a smaller buffer. We'll have a smaller delay in terms of when the information is played out relative to when it was sent across the network. However, more packets, a larger fraction of packets, won't arrive by the deadline and they'll be treated as loss. And what's implicit in what I'm saying above here is that if packets don't arrive by the deadline, typically we'll treat them as loss and not try and recover it. The reason for that is recovery takes time. You need to tell the other end that something's been lost and it needs to be retransmitted. And usually for a real-time interactive scenario, there's simply not time to tell everyone to hang on and to go back and get the information. So packet loss is simply skipped over and we'll do without it. That will then just be a little bit of a glitch in the conversation, or there'll be a little bit of an or something like that, and it will be okay. So this is a playout buffer, and how a playout buffer works to provide real-time transport across the internet on top of a best effort network service. We should talk a little bit about an overall VoIP or Skype call, because we've seen a key component of it here, the media playout buffer, how to provide real-time. But there are a few other components of a real-time session, something like a call, like a Skype call. There's the playout buffer technique to provide real-time transport. There's also actually carrying the media across the network. It has to go in the packets in some kind of format. I'll tell you a little bit about that as we work with RTP. There's also session description information, and this really has to do with the format of the media. There are many different kinds of codecs or possible encodings of voice and video. They all have different trade-offs in terms of their quality and their bit rate and other parameters, just for the kinds of components you have available to play them back. There are different alternatives. The format of information can be specified with standards such as SDP, a Session Description Protocol. I'm not going to talk about that in these slides. This is really just a bit of descriptive information. What I will talk about, though, is the final missing piece here, and that's something for call setup. We're just talking about the media so far, but you don't just start sending voice samples to someone across the internet. First you call them up and you set up a call before you send the media. This is the call setup or the signaling with a protocol such as SIP that I'll talk about in a minute. Now, I also want to point out that a real-time session, such as a VoIP call or a video call, can have many other attributes to it beyond what we're talking about. As well as audio, you can have video together in the combinations and even other data. And you can often have multiple parties, a group call, mobility as people move around and so forth. These are all important features. But in what we're talking about, to keep it simple, I'm really just concentrating on an audio call across the network. So let's talk about that, and we're going to go through just some of the pieces of our scenario here. And the purpose really is to pull it together so you have an overall sense of how it works. What I'm going to do is move from the bottom up. So we've talked about the playout buffer. Now let's talk about the information that goes in the playout buffer. That's the media. How are we going to carry it across the network? Well, media is often carried with a protocol called the Real-Time Transport Protocol, or RTP. It is really quite a simple protocol. It's providing a little bit of a wrapper. You can see the header of it here. And RTP really carries media samples across the internet with this format, all inside a UDP segment. So it's just really a packaging of the right information. The header here tells us what a lot of the right information is. I've shown the header here. The media comes after it. And there are a few features to note which you would think are pretty useful for real-time transport. There's a payload type. This tells you the media format, so you know what kind of information follows. There are various standard formats. You might have heard of MP4. I'm sure many of you would have heard of MP4. Many fewer of you would probably have heard of a standard such as G11, which is just a way of encoding audio samples without the kind of compression that MP4 gives you. So it's a simpler standard for voice calls. And it's quite widely used. As well as the payload type or the media format, there's other information. Some of the key information is this information here, the timestamp. This is crucial for knowing when to actually play out those samples, right? So this is something that didn't exist in UDP and is really crucial for the real-time transport of media. And finally, I mentioned there is this sequence number. This is really a RTP packet number, but it's going to help us work out if we've got the packets in the right order, if there are packets that are missing and so forth, what's going on, to allow us to deal with a little bit of loss. There's other information in here. I'm not going to go into it. You can look at a little bit more information in your text if you would like, but it allows for synchronization when you have several streams that are part of the one call and other things which are pretty useful for multimedia. Okay, so now we've done the media itself. What I would like to talk about now, just to complete our picture, is the signaling for the call setup. The signaling for many VoIP clients out there on the internet is done with a protocol called SIP, the Session Initiation Protocol. This is an open standard for establishing voice and video calls on top of IP and managing them in various ways. It's just as I've said, but just to make clear, it's about the signaling. The media itself is carried with RTP, as we've seen. I also want to point out, just to be clear, that this isn't Skype that I'm talking about here. Skype uses a proprietary protocol for all of its signaling and even carrying of media. So it's something whose format is not definitively publicly known. So actually I can't really talk about it. But SIP and RTP are widely used for many VoIP clients out there. Here's how SIP works for the call setup signaling. It sends fairly simple messages, so it's really a little HTTP-like in that you send a simple command. These are often done with text, and you'll have a little status code reply. I'll show you how the call setup sequence in a moment. The SIP messages, interestingly, run on either UDP or TCP. Kind of interesting because one's unreliable, the other's reliable. So, but SIP was done in a way to be a little agnostic to what's below it. And also in this picture, I'm just going to talk about two clients, one of whom is calling another one. But actually, if you look at the real SIP standard and how it's used in practice, there are often parties who can come in between here who relay the information. These can be proxy servers and registrars. They help connect all of the pieces when you're trying to find out where someone's actually located because they're on their computer at home instead of at work or vice versa, yet you still want the call to go through. They don't matter for our simple setup. So for our simple setup, let's just say the person on the left is calling the person on the right. What happens? Well, the first message that gets sent is an invite. And after the invite reaches the receiver, we'll get status code information back. Actually, the first optional message that goes back is something to tell you that it's ringing. So this way you can get your media player on the left-hand side can play a ringtone to tell you that your message has been received at the receiver and it's now ringing on the media player. Assume they pick up, then you'll get an OK, meaning the call is on. So here someone has answered the call. And just to complete the handshake, there's also an ACK that's sent in the other direction. At this stage, both clients are connected to one another, and you can see I've already drawn in here the flow of media via RTP packets in the middle. Our call is going in a way, and we're happy and having a great conversation. Eventually, someone will decide they've had enough and hang up, and when that's the case, one side will send the other a message called bye, goodbye. Let's just say, so this is a hang up here. Either party could have decided to hang up. This is just what we have here, and there'll be an ACK, I think. I think there's an ACK for this, or maybe it's an OK. All right, OK. Not quite sure. We'll see. Let me clean this up. OK, it was OK. Great. That was the answer. So here's the overall scenario, and we've now seen all of the pieces that are needed to put together a voice over IP call, from the signaling itself, which is separate, to the media, the voice samples which are sent across using RTP, to the playout technique. So now you have an idea how to actually implement and run a real-time transport over the internet.